Okay, we are live now. Welcome
Woohoo.
back to the PES Extra Help session number 7. In this one, we're going to spend a long time on the assignment. To start with, anyone that's new to this, you can join the Hangout. So if you're watching on LMS, Josh,
Yeah.
mute your thing. Oh, I think it's me. No, it's me. Ignore me. Anyone that's watching on LMS, open it up on YouTube because then you can access the chat. If you want, you can join the Hangout by clicking the link inside the chat on YouTube. I think the Hangout is a little clearer, the video. Both places you can type. If you want to talk, just unmute yourself and talk. I think there is a limit, so if there's too many people, we'll start pushing them out and then they can watch it on YouTube instead. We can just do questions through there. All right. Is there anything you want to add, Josh?
Nope, sounds pretty good.
Cool. All right, so the first thing I'm going to do to start off with, just until everyone gets here, just in terms of debugging your code. So a lot of people are just writing code and, well, the first debugging thing is that you should be compiling often. But other than that, you also should be debugging it. So checking small bits and seeing if they work. Now, one of the best ways to do this for now, we're going to look at testing in week 10, I think it is. For now, we can use our defines that we learnt this week. So these things. So you've seen in the labs that we could define a letter to mean a number. So whenever I used n in this code, 6 will replace at compile time. Okay, I'm just going to mute you. All right, so I can just define debug and not give it a number. This is really handy when you're writing your code and you want to just test it rather than actually run the whole thing and have the final output. You may want to add things like testing some output, testing your arrays, and so on. So this quick example here, we've got hash include math.h, hash include standard.io.h. We've defined n to be 6. We've defined this macro debug. We haven't given it a value. We've got a function prototype for a sorting function. What it does is irrelevant. I haven't actually included it, but it sorts an array. Okay, let's say. We've then got main. As you've seen in the labs, we create an array on the next line, so here. And we create a integer variable x and initialize it to 5. Then we do the power function. So this function here basically takes the base and the exponent. So this would be x squared, and then stores the result in y. Josh, can you just mute people when they come in?
Sure.
All right, so when we do this, we don't know if this worked. So a good idea is to print the result out. So I can printf y equals %d/n and then give y. So this line here will check if what I wanted worked. However, when I want to actually run my full program, I don't want this here because this was only for testing. But if I delete this and have to go back and test it again, then the problem is that I may have to add this and get rid of it and then add it again. So what we can do is, or we have to go through our code and find out which lines to comment out. So what I can do instead, with this define up the top, so this define debug, I can write if define debug, then print out this testing line. We then add an end if to say that this condition ends. So while I'm debugging, I have this up here defined. So I'm printing out all my variables after important steps. So this might be an important step that you don't understand what's happening and you just want to check, is y the value I expect it to be? Did it round? Did it do something unusual? Now, a big one that I've noticed a lot of people ignoring is arrays. So our array is up here. Okay, so I call the sort function on it, which sorts this array in order, let's say. You're not too sure how the sort function works, but that's okay. You just want to see if it works. So we can't do printf some kind of array. We can't print the whole array like that. Okay, we have to use a loop. So what I do is create a testing for our array. So if debug, then what I do is I put some braces here just to limit the scope of I, because if I want to create another I here, then when I'm debugging, it will try and declare I twice, which is not what we want, so we limit the scope by putting the braces here. I then print out what the variable is, just to make it nice, like I did up here, y equals, and then the variable name. And then I just do a for loop, I equals 0, I less than n was defined as 6, which is the size of our array. So this is 6. And then I add 1. So basically I'm going through this and printing the value of the array each iteration. And then I print a new line just to be neat. And then end if. Now I can copy and paste this wherever I need to check if my array works or not. So if I'm unsure about some values, let's say I do another complex equation here, I can copy and paste this and put that here as well. Then when I actually want to submit my code or check if it works without debugging, don't have to go in and comment all of these lines. Rather, I can just comment out this. Okay, and now it's not in debug mode. So what that means is that all of this will be ignored and all of this will be ignored. So then we just have our program, which is int r, int x, int y, and then our sort. So this is a really helpful feature for testing your code as you go along. So if you do this, and if you have this in your assignment, we'll be really happy to see that, because it shows that you're really testing your code and you're not just guessing. Okay? And you can put whatever you like in your debug information. Just make sure to comment out the debug when you submit it, because this will all be ignored, but we can still read that you were testing your code. Does anyone have any questions about that? I can't really see the chat windows. Josh, do you want to add anything to that?
No, I think what you covered is pretty much hits the spot. I guess it's just a nice way to be able to really test your code and still keep it neat at the same time. And also as well, if you are trying to test your code and you don't use this define debug, it's really easy to forget where you're putting out the print statements in your code. So you might get these random print statements you have to search for, whereas you can just comment out define debug and away you go.
Now, I'm just going to pull the assignment up. If you have any questions, there's two places to chuck your questions, or you can unmute yourself and raise your question. If you're in the Hangouts, there's a chat. If you click the little like talkie box thing on the left-hand side, or you can put your questions in YouTube's. Cool. So if everyone's all right with that, that's pretty good. So now let's go have a look at the assignments. I went too far. Okay, let's get the assignment file up. Now, just one thing with the assignment also, I put this up on LMS today. So with the assignments, the output shows 3 decimal places. Yours should only be 2. So don't worry about that. Let me get the assignment up. Okay, cool. All right. So if you've got the assignment sheet, have it next to you. It will make it easier to go through. So I'll quickly show you what I mean. So on the assignment sheet, there's 3 places here on the exponent. However, yours there won't be. All right. So if you go to page 5, we first look at the function main. So the first things first is printing your name. Now, everyone did that pretty much correctly in the first assignment. If you got a comment about your formatting being wrong, double check it. None of you should lose marks here. But just
unless you put someone else's name.
Yes, unless you put someone else's name. You shouldn't get this wrong, okay? And I'm pretty sure most people got that right, and no one printed John Smith, which I was happy with. All right. So the next step is the program asks the user which circuit they would like to evaluate. So here, we know that there's 2 types. There's one, which is parallel, or 2, that is series. We need to store that result somewhere, so we can create a variable for that. I've just called it T, just because of the diagram. But you can call it whatever you like, make it more meaningful than T. You also need to handle the case if they enter something wrong. So if they enter 0 or 3, you need to ask them again. This is very, 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 very similar to the first assignment. Okay? So we did basically the same thing as the first assignment here. So you shouldn't have much problem with that. You also need to collect 3 other things. You need to collect the frequency, the voltage, and the number of components. These are all ints. Okay? Now, with this, you do not need to... you do not need to worry about the frequency being wrong, or the voltage being wrong, or the number of components. You can assume that they'll be right. Okay? So if you want to add the testing for it, that would be good. But you don't have to. Okay? It's not something that we're going to check. All right. So I'm pretty sure everyone should be able to do this without any troubles. It's very similar to the last assignment and very similar to what you've been doing in the labs pretty much every week. This one here is similar to first assignment. Oops. To assignment 1. And these ones here are even simpler because you don't need to check the values. So just declare your frequency and then grab it from the user. Declare your voltage and then grab it from the user. Declare your number of components and then grab it from the user. Now, one thing that some people asked about is the voltage. So the voltage has 2 components. Okay. Now, we know for us that the voltage, let's say they enter 6, 6 is the real part. So we've basically got this. Okay. The complex part is 0 in our case. Now, the reason that the J is there is to indicate that this is the complex part in maths. We don't need to do the J because we are storing it in 2 separate variables. Okay, so you don't need this J inside your actual variables. Okay, when you print them out at the end, you just add the letter. It's purely for the mathematics, because if I had, say, 6 as my real part and 1 as my complex part, but I don't have the J, then I think you can work out that that would be 7. So this is why we need to add the J, or so in electronics, you'll see J. In normal mathematics, you'll see I. I think usually without the dot as well. The reason for the J in electronics is because I is usually used for current. Okay? So the J you do not need to store, you do not need to do anything with. It's purely for the maths to show when you use mathematics that they're different, but you are storing them in 2 separate variables. Okay? In the next question, I did give you the hint that it's 0. That's the reason why it's 0 as well. All right, so let's go on to part 3. So last week in the Hangout, we talked about this ugly structure. Okay? So we created a variable. Here I've called it something different. Here I've called it R of size 6. It's got pointers in it. And I forgot to put the pointers there. Pointers that point to doubles. For each one, so for the first one, we need to dynamically allocate n+1 spots for it. This first one is referring to the impedance of the real part. The second one, we need to dynamically allocate n+1 spots for it. So this is using malloc, and this is our Z complex. So you need to do malloc 6 times. Now, you could do this by putting a whole heap in a row, which would be the inefficient way. Or you could put it in a for loop that goes around 6 times. To start off with, if you're stuck, just do them one after each other, else do them individually. Okay, so the reason that it is n+1 is because we need the real part of the impedance for the first component, then the real part of the second component, third component, and then we have the total up here. Okay? Now, one other thing to remember is that because we've got n+1, the last index is n, the first index is 0. Okay? Does anyone not understand that? Or still stuck on that concept? Any comments on that? I can't see. Why is my voice echoing? Oh, because what if they enter here? Okay, so there's a couple of questions there. So no, you don't have to deal with if they enter EF or 4.3, just if they enter a wrong digit number. Okay, so if they enter 0 or -5 or 200 or 3, you don't have to worry about strings or anything like that. Okay, we're not expecting that. Okay, so I'm just going to quickly explain this again because we've been asked to explain it again. So in the third part, we create an array of pointers to doubles, okay, which is this here. Okay, and this is what we covered in the last live stream. So basically, if I had another example and I wanted to create an array of ints, let's say, and I want its size 8, then how I would create that would simply be int star x 8. Okay, and that would create an array of pointers of type int. That's not what we want here. We want doubles and we want 6, but I think you can understand the relationship there. Okay, I'm not going to give you the full answer. So we create this array of 6 and it has pointers. When we create this, so let's go back a step. When we create this, this is not pointing to anything. Each one of these in these arrays aren't pointing to anything yet. So what I need to do is basically for each one, so let's say x0, it's an int pointer. So I can then use malloc on this. Malloc size of int times however many I need. Let's say in this case it's k to make it different. Okay, and this would create one set, one row for our array. Okay. Then I need to do x1, x2, x3, x4, x5, x7. All right. So in our case, same thing. We have 1, 2, 3, 4, 5, 6. Now you can do this in a loop if you like, but just also remember that you need n plus 1. So when you do your size of times something, it's not going to be times by n, it's going to be times by n by 1. Oops. All right. I can't see the chat. Does anyone not understand that? Is anyone stuck on that part? No, I don't mean that. So when we had to create this, do the malloc, let's go here. So if I want to, let's do a simpler problem. So if I want to create an array of size n. So I scan off the user and I grab n. Okay. So to use malloc, I need to grab a array or whatever. To use malloc, we need to say the size of the memory times by how many we need. So if it's an int, each int is 4 bytes times by n. So when we use malloc, we use size of int. This is pointing to ints. We don't want int pointers, we want ints times by n. Okay? If we wanted floats, then it would be float star array equals float star malloc size of float times n. Does that make sense?
Yep.
So for us, Shabazz? Yep, makes sense. So for us, we've got one difference is that it's going to be this. Let's say equals, it's not float, but I'm going to do it that way anyway. Blah, blah, blah. Because it's an array of pointers. All right. All right. Has anyone else got any questions about that part? So I know that part was quite confusing. All right. So now that we've got our array like this, we can use it like this. So we can specify the row and the column. This is really useful. You don't have to use it this way. You can use pointer arithmetic if you like. But this will make it easier. If you use pointer arithmetic, then you need to add to your address. So let's say A4 plus 6, and then dereference it. If you wanted, say, 4, 6, then that would give you that spot. However, do we need to store the pointer returned by malloc into some other pointer? No, you've got an array of pointers. So it should be stored here. Your malloc, the result should be stored here for each one. It's a double. The reason I was using int is because I don't want to give you the full answer. You should be able to take the difference, tell the difference. All right. So you can use pointer arithmetic, which is slightly faster to access particular variables. So this one would be A4, 6, because remember this starts at 0, so this is 0, 1, 2, 3, 4, 5, and then we can add 6 to the address and then dereference it to grab or set that value. However, there is an easier way, which is using this. Okay, so for your multi-dimensional arrays, you can use this notation all you like. We didn't do a lab on it, but it was covered in the labs and also in the last live stream and in the lectures as well. So if now I need to go back up here and I got a 6 from the user. Okay, so what I want to do, given our big array here, I want the vreal total, which is the last one, to equal 6. And I want the v complex total to equal 0. So I can use these variables to do that. I know my total is at n, okay, the nth index, because we've got n plus 1, 0 to n. So if I had another array and I wanted to put something in 2, 6, I could do that. Okay, or I could put a variable there. Yeah. So that means that whatever was in X will be in 2 and 6. Let's say this is the 6th index. So if I want to put it down here, I can use these two. Because 4 is the real, and 5 is the complex, and n is the total. Okay? So we all know how to store our voltage. Just type yes if you do. Just give some feedback.
Yeah.
Cool. Yep. Cool. Cool. All right. So the next thing is fairly simple. 4 and 5. So this is a lot more simple than the one above because it's pretty much the same thing you did in the labs. You dynamically allocate memory of size n this time. So the reason we only need n in this one, we need n plus 1 in this one, is because we need the total in this one. For the components, we only need n components. There's no such thing as the total component. So we use malloc again, dynamically allocated memory. We create a pointer to point to that. And we create an array of ints. The next one is size, which is going to be very similar to the one above, except for doubles. It has the same size in terms of number of elements. It's just a different size in terms of the size of the elements, of each element. Okay? So you need to dynamically allocate both of these, and they're going to look very similar. All right, so that's 4 and 5. Let's get on to number 6. All right. So number 6, we want to use pointer arithmetic. So with our lab 6, we did this many, many times in lots of our functions. And basically the way we did it was we made a copy, or we made a copy variable, let's say. We then point the copy to the array, and then we iterate n times. So this is a for loop. And every time we go around the for loop, we add 1 to the copy each iteration. So let me get up the solutions. An example. So in lab, let me find a good example. Here we go. Sorry, I'm just trying to get a good example. Here we go, me. In the lab, we did something. So, let's do this. So you don't have to do this in a function, but in the lab, we did something that looks like this. So this is what we're referring to when we talk about pointer arithmetic. So where's my pen? Here, we create a copy, so we don't lose the start of our array. So remember, this points to the start of the array. Then this one's for summing. For our case, we are asking for the components for each of and the sizes. So we don't need the sum or anything like that. And here instead, it's going to be a scanf. Now, some people may want to do both of these at the same time. Well, I think you have to. Yeah, you do. So you're going to have to do that and that at the same time. So what you need to do in this case is create 2 pointers. So you need to create a copy of this one to point at the start here. So let's and S copy. And the reason we make a copy is purely so we don't lose the start of our array. Then we can use a for loop. We know n, the user's given us n, so we can do a for loop. And then in here, we can do scanfs and printfs and whatever else you want to do. You also have another thing that you need to consider. So in yours, you're going to need to add, you're going to have to increment 2 pointers. So both the C copy and the S copy. You're not going to have a return because it's not a function. The other thing that you have in here is you need to check if it is a, then you need to say enter the size of the components in ohms. Else if it's a capacitor in farads, or if it's an inductor in henries. I would say for ease, I would do that last. Firstly, just see if you can get all the components. So just have 2 scanfs and a couple of printfs and print it. Then you can add the if statements to check the right thing. But this question here pretty much revolves around what you did in lab 6. The only difference being that you have 2 and you don't have to do it in a function. Now, let me check the questions. There's one question here. Okay. So does that make sense? Anyone stuck on that part?
I completely understand it. Well, I think I understand it, but the way I've written it, I keep getting segmentation faults. So I'm just sort of trying to figure out what's causing that.
Okay, so if you're getting segmentation faults, what is likely happening is that your pointer here is pointing to somewhere that is greater than n. Well, actually, n minus 1. Because this one's n minus 1. Yep. So what I'd be checking if you're getting segmentation faults is how many times is this looping? So a good test for your for loop is testing the I value and printing it out. The second thing you can do is test the size of this. So if you look at the size of operator, you can actually use it to work out how big your array is. And other than that, yeah, so it's most likely either of 2 things. You're either going too deep in your iterations. So I'd be checking your I, or where your pointer actually points. I saw someone starting at 1, which means they started there instead, and they were going to n rather than n minus 1. So I'd be checking that, and I'd also be checking that you've malloced correctly, such that you've got n components of the right type, because that would be what we causing your seg fault.
Yep.
Okay, if you've got a question and you've got code to show, you need to email it, but you must be able to explain the problem. Okay? I'm not just going to fix your problem. But don't send your code over here. All right. And just tell me when you send it if you do send it. And we can go through it if it's reasonable. All right, so next we need to call the impedance function. Now, I'm pretty sure everyone knows how to do a call. Our function is void, so we don't need to store the result. And we've got all of our variables. So it's going to be calculate impedance, chuck the value in there, in there, in there, in there, in there, and there. So choice is our parallel or series, frequency is our frequency, n is the number of components, values is our values, components, and result table. Now, one thing that we did see a lot in this week, do not do this with your function call. Okay? Your function call should never have, where's my colors? Your function call should never have the types in them. Why did that not work? Okay? Because you're not declaring them when you call a function. When you go to the function, you are declaring it at the start of the function, and that's why the types are there. But when you actually call the function, you should never write the types there. All right, does everyone know how to call a function? Yep, cool. Josh, is there anything you want to add at this stage?
No, I think what you've gone through so far is pretty good, so pretty happy so far.
All right, so we're going to jump right into calculate impedance, and we'll go back to main. So let's have a look at the impedance function. All right, Antonio, can you clarify your question, please? How to function?
Just in general. How do you function in general?
Okay, well, was it meant to be a joke?
Maybe.
All right.
It is a joke.
Okay. All right. So the calculate impedance function, there's a lot less instructions because this is where we're testing your understanding. But I want to go through the maths of it. So when we get to the function, we have a couple of variables. We have our n, we have our f. So n's the number of components, f's our frequency. Yours will be called frequency. We have our choice, which I've just called c. We have our 6 pointers, which point to this big thing here. We said that the total V is, why isn't my eraser working? So a different layer. Okay, we have, that's not working. We have 6 as our real voltage, and we have 0 as our complex voltage. And we also have our components, and we also have our values. So now we need to calculate the ZR and ZI for each of the components, and we also need to calculate it for the total. So remember, this is the total. Okay, this is our +1. So how do we calculate this? So if we have a look in the lab, we go up the top. Why didn't I this PDF? There it is. So if we go up the top, we've got these equations here. Now, let's go through each one by one, and we'll do an example, and we'll get them stored. So the first one is if it's a resistor. So basically, we need a for loop to go through each of our components. So our n components. The first thing you need to check is it 1, 2, or 3? Is it a resistor, capacitor, or inductor? So you're going to have some kind of for loop that goes around n times, looking if it is a 1, 2, or 3. So if it is a resistor, then our equation is Z equals R. We can relook at that as being R0 plus J. So when we look at our first one in our loop, we see it's a 1, and we see that its value is 4. So we can simply store a 4 here for Z real and a 0 for Z imaginary. So if we look at it in terms of our notation, we have ZR is 0, and that would equal this value here. So components, sorry, not components, would equal values 0. And, oops, I made a mistake. 0, 0. And our complex part is just going to be 0. Okay, so let's have a look at that. So ARR 0 is here for the first 0 and here for the second 0. Okay, because these are 0, 1, 2, 3, 4, and so on. So 0, 0 is referring to this top part. Value 0 is 4. Because Z equals R plus 0J, it's just the same value. That's easy. The complex part is 0, so we need the 1. The 1 is here. We need a 0, because we're referring to here, and that will equal 0. Now, in your case, if you're doing it in a loop, this won't be 0 here, and here, and here. Rather, it'll be something like I'd imagine. Okay, so that is how you would calculate if it was a resistor and store them in the right place. However, if it was a capacitor, we have a different formula. So if it's a capacitor, I'm kind of running out of room, we have this formula. XC equals 1 over 2 pi FC, where Z equals 0 minus J times XC. So, let me move this down. So if we look at this formula instead, we can see that the real part for a capacitor is always 0. We also have this minus here. Okay? So now we're looking at the second component. It doesn't mean that the 2 can't be here. It's just that that's the way it's ordered here. So if I wanted to calculate 2, which would go here, it's a capacitor. So we need to calculate XC, and we need to calculate the real part. The real part is really easy. So we can go ARR 0, 1. We'll change it to an I in a second, equals 0. Because the first 0 refers to the real, and the 1 refers to, we're looking at the second component now. Yep, index 1 is the second, 0 is the first. Now, the other equation is going to be is the complex part. Because we've got the j there, we know that the xc minus xc is the complex part. So in this equation, we basically have minus 1 divided by 2 times pi times f times the value. So values 1. And that would be our value for our capacitor. However, if you're doing it as a loop, you need to change these to i's, or whatever iteration variable you're using. Okay, the last one is the inductor. So we're looking at the third one here. Once again, these could be in any order. However, if you do this in a for loop, it shouldn't matter because you can use if else if here, and you know what it is because it'll either be a 1, 2, or 3. For an inductor, we have XL equals 2 pi FL, and then we have Z equals 0 plus J XL. So simply, it would be ARR 0 I equals, so the complex part, once again, is 0. Okay, we're still looking here. Oh, we didn't put the values in. Josh, can you quickly calculate this? Given, let's say the frequency is, 60.
Yeah.
Yeah.
Which one, sorry?
This one. -1 over 2 pi times f times values. Values is 5. Please don't be a big number. Please don't be a big number.
All right, 2 times pi times, what do we say, 60? That's,
yep.
What's that value? 1?
5. It's 5.
5. 1884.954, or negative that.
188. So here we have, I should use a different color. So here we have -1884.
5.
Okay. 5.
As in 1885.
Right. Oh, sorry. So here we have -1885. Because this is 5, and we've just calculated that. Okay, so we've done these components. Now we look at the third one, which is index 2. We want to look at the complex part. Now, what would be a good idea to make it even easier for you? So I'm using these zeros and ones. You could write a define to give them names. So you call 0 real impedance, 1 complex impedance, 2, etc. And that would be a nice touch to make it a lot easier as well. So for this, we just use this formula. It's plus here, so it's just 2 times pi times f times values I, which Josh is going to calculate.
2261.95.
2261. I'm not going to put the decimal places because I don't have much room. Okay, so this is what our array looks like right now. This doesn't exist because it's 3, so this will be number 3. Is anyone stuck on that point? Me. What don't you understand, Yola?
Matt, if suppose we are getting only integers, so in that case, our complex part, the imaginary part is always going to be 0, right?
No. No. Okay, if it's a resistor, the imaginary part is always 0. If it's a capacitor, the real part is always 0. If it's an inductor, the real part is always 0. It doesn't matter if it's an integer or a double, that is always the case. Purely with the formulas. If it is a resistor, the real part is exactly the same as the value. Yep. If it is a capacitor, the imaginary part is this with a times -1, basically. If it's an inductor, the complex part or imaginary part is this, where L is your value, where C is your value. Yeah?
Yeah, okay.
Does that make sense?
Yeah, thanks.
Cool. Any other questions about that part?
Just quickly, with the capacitor, I forgot to find the inverse, so it's actually 0.00053.
Oh.
My bad.
0 what?
0.000.
Yep.
5.
53?
53,
Okay.
yeah. My bad.
I would say 5. And that's a negative.
Yeah.
Okay. Don't forget about this negative. So you can think of it as just times -1 if you want. So let's just do this cleanly on another page. So if resistor, then basically the real part equals the value. The imaginary, why is there a round bracket, the array in the bottom? Oh, that was just me drawing fast. It's meant to be like that. Okay. If it's a capacitor, the real part equals 0, and the imaginary equals -1 over 2 pi f times the value. And if it's an inductor, then the real part equals 0. So don't forget about this negative as well. And the imaginary equals 2 pi f value. Okay. Any questions about that?
So Matt, we are accepting 3 different values, right? So if the component is resistor, then a value for it. If capacitor, value for it. Inductor, value for it, right? Each value has two different parts. One is real one and the other one is imaginary one, right?
Okay,
Now,
so
if we want to...
No, stop. So value is its size. Value is its size. We don't want its impedance. So this is its impedance. Okay? Value is its size. So the size of it for a resistor is in ohms. The size of it in capacitance is in farads. And the size of it in terms of an inductor is in henries. This is one value. So when we get it from the user, we only get one value. We turn it into impedance, which is two values. So we don't get two values from the user, we get one, which is the value, the size of it.
So when we get a value from the user, for example, for resistor, then we have to, or maybe for capacitor or inductor, then we have to perform one operation twice, one for real one and second time it's for imaginary part, right?
What do you mean? So when we get it from the user, so we get one value from the user. Okay? And then we take that value and turn it into two values. This is called its size or value. This is called its impedance. Okay? So any value.
The assignment says calculate the impedance for both real and complex part for each of the components, right? So, so that means we have to find the impedance for like 2 times, right? Can you please elaborate on the same point?
Pardon? You're not making sense. So calculate the impedance for both the real and complex part for each component. So you're calculating the real and complex, which we've done up here, for each component. So there's one value per component. Yeah? Does that make sense at all?
I'm still a bit confused.
Okay, so I asked the user how many components they have. They say 6. Let's say a small number. They say 3. I then ask them what type of component. They say it's a resistor by putting in a 1, and then they tell me it's of size 60. Then they say they've got a capacitor by putting in a 2, and then they say it's size 4. Then they say they've got another resistor, which is size 2. Then these all are in one array called values. So I've got 60, 4, and 2. And these are in another array, which will have 1, 2, 2 in it. So this is my components. This is its values.
Matt, it should be 1, 2, 1.
What? Oh, sorry. It really doesn't make a difference, but yeah. Okay, so then what I need to do is for each of these, I need to calculate the real and imaginary part and put it in my results table. Okay, the first two, Z real, Z imaginary, and this will be component 0, 1, 2, 0, 1, 2. So for this first one, I know that the real part, because it's a resistor, will be 0, and I know that it's a resistor, so the imaginary part, the real part will be 1 and the imaginary will be 0.
60
the second
and 0.
one,
The value is
60,
60, yeah.
the second one, we have 4 here, but it is a capacitor. So we know that the real part is 0, which we've calculated. Yep. Real part 0 because it's a capacitor. And the imaginary part is going to be -1, 2 pi times 4. Times f times 4. Which Josh is calculating right now.
-0.000663.
0, 0 is something. Then we get the next component, and we know it's a resistor, so it'll be a 2 and a 0. So here we've calculated both the real and imaginary and stored them. Does that make sense, Ella?
Yeah, thanks.
Cool. So let's use that. There's only one value coming in, but you get 2 values when you calculate the impedance. All right, there's another question here. So earlier, if we're using the loop, if we're using the for loop in part 6, no. Okay, so one question that we've got here is that if we're using a for loop in part 6, we said that you need to use pointer arithmetic to do this. And the second thing is that in part 6, you're not actually touching the results table at all. So in part 6, you should not have, you could have done it that way. I don't know what happened there. In part 6, we shouldn't see this anywhere because we want to see you do it with pointer arithmetic. You can do it with that, but the assignment says not to because we want to see if you can do this. However, to make it easier, yes, you can do this here when you do your loop. When you do your loop here, you need to be using pointer arithmetic. Here, you don't need to. It's up to you. If you want to use pointer arithmetic in this one, you're welcome to. Does that answer your question, Shabazz? Yeah. So where you're referring to part 3 for the loop then. Oh, this loop. Okay, yeah, you can do either. That's fine. Yeah. You can do either pointer arithmetic or I. Either one is really easy. Because it's only 6 in the array. Yeah, so if you wanted to, you're welcome to do something like ARR I equals malloc blah blah blah. That's fine. If it's in a for loop. But not part 6. Cool. All right. Once again, if you want, Josh is going to put the chat, the Hangout link in the YouTubes if you want to join the Hangout part.
That's exactly what I'm going to do.
I knew you were. You read your mind. Okay. So I'm just going to copy these values over to my table down here. 4, 0, 0, 0, negative 0.0005, and 260. 61. Okay, my n is equal to 3. So let's get rid of that, and then we've got our total. All right, so this is part 2. So we've now filled up all of these. Okay, so in terms of what we've got, we've got these ones, and we've filled all of these up. Okay, we've gone through each of our components and done all that. So this could be n long, depending on how many components the user's put in. So it could be really long or really short. It depends. As a limit, it should work for 1. It shouldn't work for 0, though. If you've done electronics, you should know why. All right. So our table will look something. Ugh, this is going to end badly. Like that. Kind of. Let's just say that. Oh, didn't mean that. Something like that. Okay, so we've got our table. We've got all the values in. Now what I need to do is, if it's in series, I need to calculate, well, if it's in series or parallel, so this is part 2, I need to calculate the totals for impedance, so these two values. Now, how this works, I'm actually going to go through the examples that are on. So doing this by hand is a bit of a pain. So if you're doing electronics, I feel sorry for you, because it's actually really easy once you've got this program. So if we have a couple of components, let's say we have our impedance values and we have 0, 4. Let's make it simpler. We have 0 plus 4j, and we have 4 plus 0j, and we have 0 minus 2j. Okay, so this, in your array, it looks something like that. Okay, but I'm just going to write it in mathematical notation. So this is basically if they're in series. So we've got 3 components, impedance of 0 plus 4j, 4 plus 0j, and the third one is 0 plus minus 2j. Okay, for this, we have a formula which is on the assignment sheet, which is zt z1 plus z2, and then z2t equals zt plus z3. Now, we also know from our last lab that, I don't have it here. It's okay. So we also know that if we have 2 z1s plus z2s, then we basically have the real part is just real 1 plus real 2 plus j imaginary 1 plus imaginary 2. Okay? So what we can do is make it into a sum, as I've suggested. So we can go sum imaginary and sum real equals 0. Then what I can do after that is loop. and I can take this value and add it to my sum. So I can go sum real equals, actually, I'm going to do, we can use our, because we've got functions for this, we'll use our functions. I can go complex addition. Now I've got to remember the prototype for that. So we've got two numbers that we need to add up. So Z1 is going to be our sum. So sum real, sum imaginary. Then what we're going to add it to is going to be this number. So we're going to take some value from the table. I'm not going to give you what that is. Table. I might do this again. Okay. Sorry about this. It's hard. Only a small screen. So I got sum addition. We're going to complex addition, and we're going to send in the sum real, sum imaginary. We're then going to take the result table. We want the real part first, and then if it's in a loop, it's going to be I. Then we want the imaginary part and sum I. And then we need somewhere to store the result. Now, if you have a look at your function, it's a pointer, so we can store the result in sum, and that's perfectly fine. Okay? So if we loop this, basically what we get is 0, 0 as our sum. On the first iteration, we add this to it, 0 plus 4. So now our sum will equal 0 plus 4j. Then on our next iteration, sum is going to equal 4 plus 4j. And then on our third iteration, we get 4 plus 2j, because we've subtracted 2. So this is for series. So for series, we just use a simple addition. Okay? So let's go back here. So yeah, I think the series, it's fairly simple. I'll just double check that I haven't missed anything. Okay, that's pretty much it. So if your circuit is series, you create two sum variables, and then you just keep using that complex addition function and up the sum. Okay, so sum's fairly simple, and then you'll get some result. You need to put the result in here as well. Don't forget that. Okay? Because if you're using sum, then you need to chuck the values back in here. Does that make sense? Just type yes if it does. Yeah, cool. Just check the other chats. Josh, do you want to add anything?
No, I think it's all pretty good there. For series, it's pretty nice.
It's pretty nice. Cool. Everyone's saying yes. I'm happy with that. All right. Now we've got the ugly one. So the ugly one, I've actually given the working out for on the lab. So what we might do is actually go through the example. So the ugly one is when they're in parallel. So this worked example that you can compare your answers to is in parallel. Now, because there's a worked example, use it. So you can check your answers as you go along. So if you're up to this step where you're calculating impedance, you can check, does it equal negative 8.842, etc., etc. Okay, so use that example. But let's have a look at it. So in this case, we've got our components in parallel. Now, this one's the harder version. So if the user wants a parallel one, we need to use this formula. So Z total, how do I write it on here? I use the same notation. ZT equals Z1 times Z2 divided by Z1 plus Z2. Okay. And then from there, you can keep summing that. So Z2T would equal whatever, ZT times Z3 and so on. Yep. Oh. Very long my interface. Okay, so this is parallel now. So as you can see already, it's a lot more complex because we have 3 equations. So in this one, let's go to my example. We have our components. The first one is 40 plus 0j. If you want to follow along, this is the example on the sheet. Minus 8.842j. And then we've got 0 plus 7.5.4j. Okay. So each one of these refers to a different component. Oh. All right. So similar to before, we want to basically have some temporary variables to store the results. So this time you can do it with 8 or 6. It is up to you, whatever you feel more comfortable with. So the first 2 is going to be the same as before. We're going to have the summing variables to store the sum of the results. So sum real, sum imaginary. What we also need is, because Z1 is used at the top of the division and at the bottom, we need to store the top temporarily and the bottom temporarily until we've got the division. So we're going to create a temp variable for multiplication. And because we need the real and the imaginary, we need 2 variables. And we also need a temp addition. Now, we don't need a temp division because we can store it into the sum. However, if you feel more comfortable, you're welcome to create one for the division as well, if it makes it make more sense to you. Okay, that's up to you. So in the question, I'm pretty sure I made you skip a step. So in the question, So in the question, I suggest that you start by setting the sum to the first value. So sum is 40 and 0 at the moment. Okay. Yeah, that looks right. Okay. Then what I say is iterate through from the second to the last one. So what you're going to do here is you're going to have a complex. Now the order doesn't matter. It's up to you. You can do the addition first or the multiplication, because you're going to restore the result of these in two different places. So let's do the addition first. Let's do the multiplication because it's more logical. So let's do the complex multiplication function first. And you're going to have, sorry. You're going to have to send your sum real and your sum imaginary. Then you need to use your result table to grab your values, blah, 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 as before. This will obviously be in a loop, so there'll be an I somewhere. And this will be a 0 and this will be a 1. And then on the last two will be pointers, so addresses. Did I remember that in the last one? Yeah, I did. Now, here is important. So that we don't lose the value of Z1 and Z2, so we can still do this addition, we store these in the temp multiplication variables. Okay? We then call the addition one, which will look very similar. So it's going to be sum R, sum I, the results table, blah, blah, blah. And then the address of the addition one. So at this stage, we have all of these. So we have the top and the bottom of the equation. Okay? So these two and these two. So now we just need to do a division. And our inputs this time are not going to be sum, but they're going to be the multiplication, real, multiplication, imaginary, addition, real, addition, imaginary. Oops. And our results will still be stored in our sum. Okay? So this is just happening in a loop, starting from the second one. Okay? And you can just keep looping that. And then once you've done, you can put this sum into here. Okay? Because the sum will be the right answer. Any questions on that? If it makes sense, just say yes. Josh, do you want to add anything about that?
Not that I can think of.
I need to breathe. All right. And that's that in summary. So we've got our addition, temporary variables, our multiplication temporary variables, our, I don't know why I call it C, but sum. And then we've got the complex addition, the complex multiplication, and the complex division. And they just happen in a loop. And you just need to put the correct parameters in there. Now, this isn't the only way to do it, but it also needs to be done properly. And then store appropriately. So they should be somewhere like that. All right. So now we go back to main. Bye, Connor. See the message in the YouTubes. So now let's go back up to, where's my sound check? Yeah. All right, so now we go back up to main, and we've done 7, which was that complex impedance. So now we're up to step 8. So now we're talking about the total current. All right, so I'm going to pass it over to the audience to type it out, because I know there's a lot of people doing electronic engineering, and if you don't know what the answer to this is, how do we calculate current using Ohm's law? Come on, who's going to win? I'm going to type it first. Yay! Yes.
Ooh, virtual reality.
So with AC, AC, it's actually V over Z, because R is for DC, because we're talking about resistance. Now we're talking about complex resistance or impedance. So it's V over Z. So I total is going to be V total over Z total. Okay? I think you can work out how to calculate the total current. It's just complex division. You have in your table, so let's have a look at our table. So it looks something like that. Blah, blah, blah. At the moment, all you've done all these. You've done the total. So in blue is where the total will be for your Z. And you've got your total for your V. So you can do V divided, you can do this V total divided by this Z total to get your total current. Okay? Now when you do this, do not divide the real by the real and the imaginary by the imaginary. Use your complex division. They are complex numbers. Okay? So use your complex division function to do this. Okay. Once again to the electronic engineers. If the components are in parallel, what is the same through all components? Yay. So voltage. And hence series would be current. So this is really nice because it means if you do parallel, all of these are really easy. If you do series, all of these are really easy. So here we got in green is this value. So if it's parallel, then all you need to do is do a loop and just copy the values from here to here. Okay, as simple as that. If it's series, then just copy the values from here to here. Okay, so you just do a loop and just basically results 0, 1, 2 to I equals your total, and results 3 I for the complex part equals the total. So that would be if it was current, and if it was voltage, it would be something very similar. Yep, and you just loop through that and set all of them. However, we need, so maybe I'll draw that again. Yeah, maybe I'll do that again. So if we're parallel, we basically have got all of this information from our table, and all we need to calculate is current. We have all the information. So all you need to do now is to get your current, it's just going to be V divided by I to get this one. Okay, so this one divided by this one gives the answer there. This one divided by this one gives the answer here. Because this is voltage, this is Z, and so you just need to calculate the current if it's in parallel. And these are all the same, so you don't need to iterate, you can just use that if you want. These are all different though. Does that make sense? However, for series, we need to calculate voltage. So that's a new formula. Well, not very new. But. So if it's series, we have all of this as the table, and we need to calculate. So we've got Z, we've got I, but we're missing the V for each component. So who can rearrange the equation? What's V equal to? Even Josh doesn't know this.
I don't. I didn't pay attention to that class. The V is equal to the voltage, right?
Yes, Josh. Okay. Yay, we got it, finally. All right.
Cool. Alex said it as well, I said, on the YouTubes.
I don't know. I think he came in like 2 seconds after.
Ooh.
No, it was very close. Anyways, so we've got V equals I times Z. So here, once again, very simple. Z times this one is this one. Now, for both of these, don't just use that. You need to use your functions you created in the lab. So here, you're going to be using complex division, and here you're going to be using complex multiplication. Okay? And it's just a for loop, iterating through each one till you get the values. All right. can see that.
See that? Awkward.
All right. So the next part is 10, which says call the print function. What's the print function look like? So the print function has three elements, three arguments, sorry, which is the result table, which should be all full now, n, which is the number of components, and then the component names. Now, the printing part is fairly easy. I don't think you're going to have problems with that. One thing to be noted, however, is you'll have 2 exponential places rather than 3. So the other thing is that I gave you some values to use originally for the width to put the component names. However, I've taken that away because yours is going to be different because it's missing that extra digit. So to make it fun, you have to work that out yourself. Okay. And then you're done. Fireworks.
Kind of looks like
That
alien
fireworks.
ears or something.
Yeah.
Yeah.
All right. I'm just going to check if I got emails. Yes, the flowers. All right.
Terrible style. Just saying.
All right. What time is it? It's 10 o'clock. All right.
Quarter to 10.
Cool. I'm going to take a quick break. Do you want to start going over the next stuff, or does everyone want to take a break? Or? It should be worth 20%.
This should be worth 20%.
No, it should be worth 2%. It should be 10 of these.
The next one's going to be even better.
The next one's hard. All right. Do you want to take a 5-minute break?
Sure.
We'll answer the next part, and I'll answer this question with an email. Do you want the elevator music?
I should. I need to find it. We can just sing it if we like.
Hey Matt, can I ask a question pertaining to the assignment?
Yeah, of course.
I found what was causing the segmentation fault, and it's when I was freeing the memory.
Yep.
Now, for some reason, when I free it in a for loop, it causes a segmentation fault. But if I write out all 6 without a loop, it doesn't cause an issue. And also, the for loop seems to work perfectly fine until I've got for I equals 0 until I, while I is less than 3. It works for 1 and 2, but as soon as I put in I is less than 3, it causes a segmentation fault or a glib detected, whatever that means.
Yeah, so your stack collapses.
Yeah.
Are you sure you've allocated all that memory. So what I do is
Well, I've allocated memory for each of the
so in your loop
6 positions of the array.
to debug that in your loop. What I do, I put your if debug, if def, sorry, in your loop, and what I print out is to check if you're freeing something. Is put a printf. So let's say this is your free. Put a printf and print out the address of what it points to. Okay. Because if it gives you null, then it means it's not pointing to anything. Or it still will point to something. Yeah, no. Yeah, I would check that anyway.
But then shouldn't it also cause a segmentation fault by me writing out free results 0, free results 1, free results 2?
Yes, it should.
But it doesn't. As soon as I remove the for loop and write them all out one at a time, my code stops having problems.
That I can't help you with. I don't know. It's probably probably something earlier that's causing that.
Well, that's what I thought, and I've been working on that for ages until I decided to comment out the free section to see whether that, and lo and behold, commenting out freeing the memory stops all segmentation faults.
I'm not sure what you're doing to cause that, but that's fine.
I'll email you the 2 bits.
No, don't.
Don't?
You can work it out. Yeah, you can work that out. You've already told me the problem. That's why I'm going to tell you back. It's just to debug it. So, yeah. All right. Is Josh back? I think everyone's sneaking away. So
Yes.
they've got their assignment help. But, has anyone got any more questions about the assignment? Luke, you filled out the survey yet?
There's a survey?
I just said it in the chat.
I don't see anything in the chat.
They're in both chats.
No one listens to you, Matt.
You can see it, right, Josh?
Yeah, it's in there. While you wait, Link, it helps us out to run stuff like this.
Well, I left the group call for a bit, so maybe I'm not in anymore. Well, maybe I can't see anything that was posted earlier.
Oh, yeah. That goes for everyone else. If you can, I highly appreciate it. All right, so what I'm going to do now is hand it over to Josh.
Yep.
And he's going to go over something. Oh, no. We're going to go over
Command line arguments?
Go over command line arguments.
Indeed. All right.
So this will help you out for the next lab and also for the quiz this week. So I'm going to put Josh up on the screen and let him take over for a little bit. So
Hello. Cool. All right, so what we'll be learning about this coming week are command line arguments. So what those basically are, for those of you who don't know, is when we run our code on the command line, we can actually type some stuff in after our executable name. And with the things that we type in after our executable name, we can use those within our program. So, for example, before we get into that, actually, we have two things. We have this thing called argc and argv. So what these are parameters that actually go into our main program. So here's a bit of a program I wrote before. So you'll see here how we have two parameters, int argc and a character pointer argv, which is also an array. So an array of character pointers. So we have these parameters for our main function, and argc represents the number of things that we type in on the command line, and argv is each of those individual strings. So everything that's separated by a space, we have a string representing that. So again, this is useful if we want to run our program and give it some input on the command line at the same time. We can really easily do that with our command line arguments. So what I've got happening in this program here is I'm printing out, just maximize this, there were argc arguments given on the command line. So again, argc represents how many arguments we use on the command line. So if I typed into my program, this is called comline. So if I compile my program and I run to run it, if I write in comline, just to run my program as normal, the value of argc will be 1 because there's only one command line argument. But if I write something else after it, like hello, maybe I'd put in a text file, hello.txt, a number, and another file, hi file. So what will happen is the value of argc within our program will now be 1, 2, 3, 4. So a thing to take away from that is the executable name counts towards our argc value. And what will happen in our argv, that's again the strings. So each one of these things that I type in is stored into this array of strings. So each one of these represents a string. So just to give an example, what this program does is, first off, it prints out the number of command line arguments there were. Then it iterates through each one and prints out what the command line argument was. So I'll show you an example of that over here. I don't know how well you can see, but if I typed in comline, just the executable name,
Sure.
you'll see that.
You can right-click the top and make it bigger.
Oh, yeah.
It's hard to see.
Font. Did that change it? No?
I think you applied it.
Hey. 24. Okay. I have to reset it or something. There we go. That's a bit better. Is that easy enough to see?
Yeah, it's better.
Cool. So again, if I run my comline, this program here, what will happen is it'll say there were one argument given on the command line, and the argument was comline. So again, what I was saying there is what we actually type in as the executable counts towards our number of arguments and is actually the first argument in our argument array. If I was to run it again, and I did that example, so I did hello.txt, 5, and my file.dat, again, as we were saying, there are 4 arguments on the command line. The first argument is comline, the second one is hello.txt, the third one is 5, and the fourth one is myfile.dat. And again, the reason that we use these is we can straight away give input to our program when we run our program, so at the same time. So Matt will probably go into this a bit more in his part when he talks about files. But if you wanted to deal with some files in your program, maybe you wanted your program to read from a text file, you could actually put that text file in as a command line argument. So instead of asking the user to type in the file name, reading it in and doing all that, you can actually just use the command line and do that in one go. So it can be really useful like that. Also, because we know the number of command line arguments, It's really easy to iterate through every argument we have that's given to us on the command line. And again, if I was to do it again, I can give it any number of arguments. So I can give it a bunch of different numbers. I can give it some gibberish. And you'll see there were 7 arguments on the command line, and it prints out what each one of those were. So that's where this comes in handy. Yeah, so that's the basics of command line arguments. You'll be doing that a bit of that this week. It'll also be on the quiz as well if you haven't had an attempt at that. One other thing I'll quickly mention, for the command line, if you put any arguments within quotation marks, then everything inside the quotation marks counts as a single argument. So you'll see when I run this, the first argument was comline, the second one was hello there. So what it will do normally is every time you have a space, it'll treat that as a separate argument. But if you put it within the double quotation marks, it treats everything inside of those as one argument. So basically that's all you really need for the quiz this week, and also the basics you'll need for when you do the lab this week. Questions about this command line argument stuff? And again, you pass these in as parameters to your main function. So argc is just an integer. argv is an array of character pointers, so an array of strings essentially. And did you want to add anything else to that, Matt?
No. Good.
All good. Cool. Thanks, Hila. And don't think there's anything on the YouTubes. No, awesome. Thank you.
Yeah, everyone's started to drop away now that I'm not talking about the assignment.
Yep. Will this be on the next assignment? It should be. If it isn't, you should make it on the next one. You should make them type in something, and that should be printed out at the start of their files. I don't know. Cool, so I'll hand that back over to you for some file stuff.
Yes. All right. Let me check back into me. All right. Before I start, is there any more questions about the assignment? All right. Hopefully it's worth doing this. How many more people are still here? Everyone's kind of left.
Right, right. So on the, sorry. Cool, just had a question back to me. Yeah. Sorry, I'll just share my screen again if that's cool. Yeah, so just for that question there, Alex, so the difference between argc and argv. Argc, are you showing my screen?
Yes, sir.
Cool. So argc, that represents the number of arguments on the command line. Argv is the actual string of what the argument is. If I type in online hello.txt 5 and myfile.dat, you can see that there's 4 different arguments that I put in on the command line. So the value of argc will be 4. So again, argc is the integer that represents the number of arguments. Argv is actually what stores each one of these. So for the first element in our argv array, that will have the value of comline. The second element in our argv array will have the value hello.txt. The third one will have the value 5. The fourth one will be myfile.dat.
You got another question.
If you swapped int argc and char argv, would it still work? Yeah, it would. So doesn't really matter as long as you have these two here.
No.
I'm pretty sure you can even call this something different as well.
It shouldn't. You can call it something different, but the order does matter.
The order does matter? Okay, I must be getting mixed up with the other one. So sorry, yeah. So you can call these whatever you want. That's what I was thinking. But yeah, you need to go int argc char pointer argb. Just by like convention, we call these argc and argb. Cool.
All right. Files. All right. Where am I? Around here. Cool. All right. So the next thing we're going to look at is files. So why are we going to look at files? So files are very handy. Let's say I wanted to get the data for, let's say, weather data over a year. Now, if I told the user, type in the weather data for a year for every single day, they may be very angry. However, if you said, give me a file that has all that information, they'd be happy with that. So what I'm talking about with files in this instance is mostly text files. However, it could be any file type. As you'll see in the lab, we're going to work with audio files, but text files are the most simple ones. And to make a text file that you can use quite easily, it's just .txt. You can also use .csv files, which is comma separated values, which you can generate from Excel. However, things like doc and docx or PDF, these won't work well because these are designed for the program that uses them. Okay? And unless you know how to decode them, you're going to not be able to read the text exactly. So let me give you an example. Where's my text editor? Come on. Let me get a text file up. No. So I've got my notepad here, and I'm just going to write some text in it. And the word hello. I'm going to save that as a .txt file. Screen that's in storage. So I've got hello.txt. Now, if we look at that in memory, if we have a look at that in memory, I can't make this bigger. I can't. Basically, it has the word hello, and that's it. However, if I open, let's say, a PDF, let's say let's grab your assignment sheet. Assignment sheet. Where is it? As you can see here, the text is all these weird different things that relate to Adobe stuff. And so you can't easily access the text. The text is in here somewhere, but it's not easily readable. Okay, so this is the assignment, but you can't read it because PDF is an Adobe format. And so it's made for the Adobe format. However, our hello.txt is just pure words. Okay, so when you've got a format that is for a specific program, it's unlikely that you're going to be able to read it easily. You still can read it, but you need to know how to decode it. Okay, so the common one you'll use are going to be .text or .csv, and the one that we'll see in the lab is .wave, which is audio. Okay. So there's a couple of things we can do with files. So these are the options that we've got in C to do with files. You can do more things depending on what libraries you use, but for our basic system, this is what we're going to look at. So the first one is R, which refers to reading. And this means that the file already exists. We then have W, which is for writing. And if it doesn't exist, it will create it. We then have A, which is called appending. So what this does is it will start the writing at the last part of your program, last part of your text file. So if you've got a text file, and well, it doesn't have to be text file, any file, and you've wrote all that. So when you open it for appending, it will start here rather than at the start. If you open with W and it exists, it will start here. So if you start writing, it will write over the stuff you already have. Okay? With appending, if it doesn't exist, it will create it. We then have R+, which is both reading and writing for a file that already exists. You've then got W+, which is both reading and writing. However, it is dangerous because it will actually delete everything in your file and then start again. And if it doesn't exist, it will create it. And now A+ here is both reading and writing. It will create the file if it doesn't exist. It will create. And it will start its reading here, but it will start its writing here. Okay, so these are the basic types of things that you can do with a file. Now, the other thing is that you've got a difference between binary files and normal files. And I'm going to leave that for the lecturer to explain because we won't be using that in the lab, but watch the lectures or read the lectures to work that out. So how do we open a file? So I've got a very simple program here. I've got int main. I've got this type here called file. So this file, when you use it, needs to be a pointer. You need to name your pointer. Now, one thing I have seen people do in the past is try and give this the file name. Okay? This is not the file name. This is the pointer that points at the file. Okay, so don't give it the same name as your file. So say we've got a file called hello.txt. This first argument is a pointer to a character array, so a string. So we can put hello.txt here, or we could have a pointer to an array of text if we had that. And the second one is the mode, which is one of these letters up here. Okay, so let's say we want to open hello.txt for reading. I would then put R. Now, one thing that I've also noticed in the past, it's not a character, it is a string. Okay, so make sure you put double quotes here. So if I want to open it for writing instead, I'd put a W, and so on. Then, when I'm finished with my file, I need to close it. Okay? Makes sense? Now, this is all good, but there's also a safer way to do this. So, what I'm going to do is grab these and make them smaller. Now, the problem with my code at the moment is what happens if the file doesn't exist, or something's wrong with the file. Maybe it's corrupted or something. So when I do this, I should check. So actually, I'll do this in 2 lines. You can do this in 1 line, but so to check if the file opened all right, we can compare it with null. So if it equals null, then printf error. Okay, and then we return or something. Don't close your file if it doesn't exist or there's something wrong with it. Another thing you can do with this close, it actually returns something too. So we can test that the file closed properly as well. So let's move these down. So to test if the file closed properly, we can put it in an if, that's not a pen. We can put it in an if statement and see if it equals EOF. So this is the first time you've seen that. I'll come back to that. And this would be another error. Okay, so you weren't able to close the file properly. All right. Now, this EOF is a special character, and you won't have seen it yet because it's only for files. So what it's referring to is when you have a file, you have a bunch of text in that file, the last character in this file is the EOF file, EOF character, which says end of file. So when reading, we know where the end of the file is, which is really helpful. Okay. Cool. So now let's have a look at, what should we have a look at next? Let's have a look at writing to a file. So there's a couple of different ways to write to a file. The first function we can use is if put C, and this function takes a character and then your file pointer. So this would be your file pointer. And this will be your character. So if I want to write to my file, which I called file pointer, so this is the pointer that points to the file called hello text, and I wanted to write the letter C to it, then I can do that. Simple as that. If I want to write a string, I use f put s. So you can see this is put character. Didn't you say before that it was a string, not a character? Yeah. When you open the file, this is a string. This here is putting a character. So for f open, you have a character array, a character pointer, and a character pointer. So this has to be a string here, and this has to be a string. So this is for f open. For f put C, you're putting a character onto the file. So for f open, you've got two strings, which could be W, which could be R. It could be any of these ones up here. It could be any of the ones up here. So this is for opening the file. The next function we'll look at is f put s. So this is putting a string into the file. And pretty much the same thing, except for now we're putting a string to our file. Cool. And that will type the word string into our file. If it is open for writing, so this would have to be a W or another one for writing. So read and write or writing. Okay. So, what else I want to show? I also want to grab. So another one you can use is your printf function, but your printf function swapped for files. Okay. So instead of our normal printf, for files, we can use fprintf. The only difference with this is that the first argument where does the file point for the first time you open the file, and does that depend on, yes. So the pointer points at the start of the file, except for when you do appending. Okay? So if you do appending, it will point here with A. It will point here in the file. And if you do A+, it will point at both of these locations. So file is a structure, so it holds a couple of addresses. Okay, but so file pointer is actually pointing at the file. Inside it, it's keeping a track of where we're looking. Okay, so it's got a couple of things. So I can actually look at a different place for writing and a different place for reading.
So Matt, basically, as you said, it depends on the mode. So if suppose my file exists, and if suppose I want to reopen it with W mode, okay. So
what
like
mode?
for writing,
Yep.
yeah. So
Yep.
let us
So
consider hello.txt exists,
Yep.
and now I want to open it with W mode. That is for writing purpose.
It'll start
So
at
as you
start.
said, for writing a character, if I want to write C, and
Yep.
if I'm providing it the file pointer, then when I want to write C, it will get
It'll be a,
appended at the
no,
start of the file.
no, it'll overwrite it.
What will get over it? Like
So if
how
I
will it
had,
overwrite?
it will, so say this is my text file. If I enter C, it's going to do that. Now it's shallow. If I enter
Okay.
A, it will overwrite it. So because it's a file,
Okay.
you cannot actually move stuff across. You can't unless you do it manually or you use some kind of function to do it. But it's always going to overwrite what's there. Okay?
Okay. Yeah, thanks.
All right, so fprintf is very similar to your printf function, except for you need to specify the file first. So your file pointer, and then you can do all the normal stuff that you did before. So let's say I've got a variable A, and I want to print it to the file as a decimal integer. Yep. So they're the basic, the basic ones. We're going to look at one other writing one, but I'll do that after we do some basic reading ones. Just give it a sec. All right. So now let's have a look at the reading ones. So the first one, fgetC. I think you can understand what this is. It's getting a character. Now, the only argument is file pointer. The reason being is because you need to store the result somewhere. Okay? The next one is fgets, which is a little different. So this one, you actually need a buffer. So what I'm saying with a buffer is before you use this, you need to create an array. Let's call it car str and give it size 10. The first argument here is going to be your buffer. So this is where the result is going to be stored. The second argument is how big is that buffer? So it actually needs to be n-1 as well. So it needs to be 9 because we need to store the null character. Yeah. And then the last argument is going to be a file. Okay. So this is getting a string. So you actually need to specify where you're going to store the result with this. All right. There's one other, which I think you can guess what it is. That's not what I wanted. So the next one is fscanf. And this works pretty much the same as your scanf, except for you need to specify your file pointer at the start. Okay, so %d and a. Yeah. All right, so they're the basic ones. Now, in the lab, however, we need to do some stuff a little bit more complex. It's not too complex, but we need to do basically binary operations. So we need to read specific amounts of data. So in the lab, we're looking at WAV files, okay? And they have a specialized format, as you will see, and it's all in the lab. You can read about it. So with this, we don't want cars or ints or doubles or floats because it has a specialized format. So some parts will be 4 bytes, some parts will be 2 bytes, and there'll also be, and there'll be 8 bytes for some of them, and some will be little endian, some will be big endian, and so we need to treat them differently. Now, all of this stuff will be explained in the lab, okay? But you need to know how to read it for now. So I won't explain that yet because it's more about the problem. It's not something you need to know for the subject. You need to know it for the lab though. Okay, so fread has a bunch of arguments. So let me just grab the lab up. So I'd do something similar. What's the lab for this week? There we go. Okay, so we have 4 arguments, and what we need for the first one is a pointer, okay, of any type. Now, that may be strange, but it will work with any type. And the reason being is for the next arguments. So this argument here is the size in bytes of each element to be read. So if this pointer is pointing to a bunch of ints, so let's say an array of ints, so these are all 4, and we have a pointer that's pointing to this first one. Yep. Then this will be 4, or size of 4. Then we need to indicate how many of them there are. So in this case, we have 3. So our pointer here will be of int star, and let's call it A. So this is A. Our last argument is just our file pointer. So this will now read into A 3 ints. So it will store a couple of values, let's say 4, 2, 7. If you only have one variable, let's say, so if you've got, let's say, int x, then you can do an fread the address of x for one file pointer. Okay, and so that'll read 4 bytes into X. Now, there may be cases where you need to read, say, just 2 bytes, but store it into an int. And this is where some of this stuff will come into the labs, because some of the data is only 2 bits wide, or even 3, not bits, bytes wide. And so you only need to read 2. Okay? And because it's not an array, we just specify 1 here, because there's only 1 place to store it. If it's an array, then you can put as many of these as you like. Okay? Was there anything else in the lab? Okay. The one thing to remember with this is that this is Little Indian on our system. Okay? So if you try and read a string in, it will be backwards. Okay? So if you're going to read a string, you should always use fgets, because it will be in Big Indian format. Okay? You're going to use both in the lab, because you've got some strings and some data that are in both formats, Little and Big Indian. Okay? So fread is in Little Indian on our systems because it's a Little Indian system. All right, and then I think you can guess what the next one's going to be. Which is fwrite. Okay, so fwrite is very similar. Let me just double check what we're doing. What's the lab? Sorry. Okay, so here, the first argument is any type of pointer. Oops. The second argument is how big the elements are. So for example, if we wanted to print this A, and there's 3 of them, oops. It'd be 4, 3 again, file pointer, and A, and that will print out them 3 ints. Okay, and that's pretty much the important stuff that you need for the lab for files. There's nothing too complex there. The files you'll be using are a little bit complex, but I've done all the complex stuff for you and you just need to write it. Why am I zoomed in so much? Zoom out. Cool. Is there any questions? Is there anything that you'll be discussing during the first hour of lab? Unlikely. There's next lab's quite easy. The only difficult parts, oops, is just as long as you know what these 2 are, you're fine. The rest of it's fairly easy. Okay. And we'll tell you how to use these, which values are, because it's a very, very specific format. And I've already edited the files to make them suitable. But now I won't be discussing anything. All right, so any more questions for the assignment?
Not really as of now. Need to start doing it.
You haven't started?
Not really. Not really.
Okay, well, get on to it. So anyone that's there, this is pretty much your last chance for questions to be answered. So ask your questions. I did say that we'd stay for, well, at least I will stay for another hour or so if you need. But if you don't, then yeah. Unless Josh wants to go over some quiz questions or something.
Matt,
Yeah.
yeah, just like a suggestion. Like, can you please discuss, like you both, can you please discuss how should we code things? Like, for example, how should we write a coding and some specific instructions, or how should we improve doing it? Because this is like almost week 8.
Yep.
And so we can improve in for further weeks, or maybe for like later on anywhere we'll be using coding. But something on how to improve coding, or maybe the style or something like that.
So the C style, so the C standard doesn't include style. So C's a very unique language because it is so old. So if you look at Java, it actually has a style guide. C does not, because a lot of companies started developing their own style early on. The big styles are going to be, NASA was one of the big ones that first used it, a lot of military institutions, stuff like that, around America were the first ones to use it. So there's not one common standard style. So just be aware of that, because if you get employed by different places, they will have their standard of style. So the style that I personally use depends on the solution and the client. And the style guides are quite heavy. We're not going to go over it in this subject. They're usually a couple 100 pages long. If you're interested in it, you can, there's heaps of them available online. But they are, depending on how heavy you want to go in terms of style and how strict it is. So if you're going to be working in military stuff, it's very, very strict. If you're developing, I don't know, just games or something, it's not going to be as strict. So, but however, the main things that you need to be doing is anywhere you use code, indentation is pretty much the same for most styles. The style we are trying to give you is always use braces and always tab in. But for variable names, a underscore to separate words. So your variable names, let's say, happy animals. Now, a couple of keywords that are used. Now this depends on the style, but a lot of people will use pointer. They'll use F. So this was referring to a pointer. So they may have animals pointer or something like, I can't spell animals. F usually is talking about file. So animals file. You've got iteration variables, which are pretty global. So you've got I, J, and K. If you use them in a file, all programmers should know what they mean. This is talking about a for loop with a single for loop. If you use J, you're talking about a double for loop. So this is I here, and this is J here, and K would be a triple. That's pretty global. N is used a lot. However, depending on the standard, usually you'll specify animals underscore N, something like that. But the deeper you get, and with C is massive. Like, you're only learning the basics so far anyway. And so when you get to further things like system operations and stuff like that, there'll be other common ways of doing things, but there is no set style guide for C. It is not like Java that has a set style guide. Does that make sense?
Yeah, but something more about how we should improve writing our code, maybe? Like any general instructions or suggestions?
So generally, the best practice is make sure it's readable. Make sure that it can be read by anyone that understands code and that it is efficiently coded. If you've studied algorithms or data structures and stuff like that, you can make it more efficient. But so far, most people are coding fairly nicely. Comments need to be used appropriately. Comments should be short. So when you comment, it shouldn't be more than a couple of words next to a line. Your larger comment should be up above your function or above main. I've noticed some people write really long comments. You shouldn't have massive comments. If you need massive comments, they should go up with comments should be fairly short. What did I do? No. Okay, so in terms of emailing questions to us tomorrow or the day after, so basically we've been telling you to start this assignment for quite a while. I don't mind if you send an email tomorrow to me, but it needs to be short, to the point. It needs to be something that hasn't been covered before, and I don't want to see your code. So if you've debugged it properly, so as I showed before, if you've printed out your values and you've fully tested it and you've got a real question, yes, you can send emails tomorrow. But don't say this doesn't work. Okay? I do not want to get swarmed by emails tomorrow, and none of us do. We've already given most of the help, and if it's something that's already been answered, then we're just going to redirect you there anyway. Or just tell you that it's been covered. So if you need to send an email, send it, but just make sure that it is reasonable, because we're not going to answer silly questions that have already been answered or look through your code and debug it for you. Okay. Is there anything you want to add to that, Josh?
No, I think that's pretty fair what you said there. Yeah, especially all the stuff that's covered in the stream, I think should be everything that people need to really get through.
Yeah. But
Any
yeah,
hint about
if you get
some?
stuck,
Sorry.
if you get stuck, make sure you follow the steps that I said at the start to debug your code, and make sure you're compiling often. Yes, Ella?
Any hint for the bonus one?
No,
Alright, thanks.
it's an easy one. It's a bit too easy. People have been getting it all over the place. You should be able to get it. Plus, the hint would give it away. I don't quite get pointers and functions in Lab 5 Task 2. Okay, let's have a look at Lab 5. Well, that's a while ago. Can you grab the stream and ask the person that asked about Lab 5 to come in? It's a bit easier.
Yep.
Well, I go this open. Lab 5. Oh, oops. No, don't open. Lab 5 solutions. Lab 5. Okay. Where's the I'm an idiot. I'm trying to open the PDF like that. Oh. This is the stuff in the assignment. Okay. Cool. I can kind of give the answers after this as well. Cool. Everything covered. All right.
So yeah, I asked them to join the Hangout. You also got a question from Antonio.
I've done the best. Not sure of the restrictions to get it done. As I'm all allowed to use them or not. Pretty much anything that's been covered already. Sure. Yeah, in terms of restrictions to the bonus, it's as long as you're using stuff that's been covered in the subject, it's fine. All right, so if anyone has any questions, just post them up. The person that was asking about Lab 5, can you click on the link to join the Hangout? I'm just writing up the question now. Because I don't know what I'm answering. Oops. So what I'm writing up now is just a simplified version of Lab 5, Part 2. Just to quickly go over the question that was asked. Here we go. Right. Complex addition. Set one. Real. Imaginary. So let's do multiplication. Two real. Set two imaginary. And this 3 real. And this imaginary. Let's copy this. All right. So, what is the question about Lab 5? So I've just simplified it down and we're just looking at one type. What I want to know. Okay, so we've got a question about what?
Yeah, so float 3 is a pointer, so I'm not really sure what that means.
Do you know what a pointer is?
Yeah, I know what a pointer is, but no, it's just confusing to me that I mean.
Okay, so how many things can we return from a function?
As many as you want, just one.
Just one. So how many things do we need to return?
As many
2.
as you want.
Two. Right, 2. We need the real and the imaginary part.
Okay.
Yeah. So in this function, we need to return 2 things, but if we use return, we can only get 1. So this is where pointers come in. So it means that we can return more than one thing into our function. So let's have a look at this. So we have, let me zoom out. That's too much. Okay, so here we have main. So everything inside these brackets are in scope. Okay, so they only exist in main. So let's draw a box to give our scope. And we create 6 variables. Okay. they're all type float. I won't bother writing float there. And this is Z1 real, Z1 imaginary, Z2 real, Z2 imaginary, and Z3 real, and Z3 imaginary. Then the user comes along and enters the values for Z1 real and Z1 imaginary. Does that make sense so far?
Yep.
So we enter 4, 2, and 6, 8. So in mathematical terms, that would be 4 plus 2j and 6 plus 8j. Yep.
Yep.
We want the answer for a multiplication to be stored in here. Okay? So we call our function. Okay? And the function creates 6 variables. Okay? So 1, 2, 3, 4, 5, 6. Because they're inside here. Yep. The first one's called in1 real, so it's got a different name. In1 imaginary, in2 real, in2 imaginary, out 3 real, and out 3 imaginary. Now, let me just make these a little different. So these ones have a floating pointer. Okay? The rest of these are just floats. Yep. Does that make sense so far?
Yep.
This is my complex multiplication function. And this is my main. Now, with this, the only thing that these pointers can store are addresses. So when I call my function, I pass the value. So the value inside here is 4. So I put 4 into in1 real. So this now has a 4. I take this value, which is a 2, and I put it into here. I then take this value, which is a 6, and I put it into here. And then I take this value, which is an 8, and I put it into here. The other two, I send their address. Okay, so I send this one's address and store it in here. Now I can represent that as being this. So it's pointing to it. Okay, so, and then the last one, we send it its address. So this one in here has the address of Z3 real, and this one here has the address of Z3 imaginary. Now the reason for that is because inside my function here, complex multiplication, I can't write Z3 real equals 4, because inside this function, if we have a look in this box, there's nothing called Z3 real. Yeah? Does that make sense?
Yep.
So now we have a link between our function and main. So we can indirectly change the values that are in here, even though we don't have their name. So now when I perform this calculation, so I've got in1 real times in2 real. So 4 times 6 minus 2 times 8. So we've got 24 minus 16, which is
8.
18, 8, yep. So now what I've got here is out 3 real equals 8. Now, out 3 is a pointer, so it can't actually store this value. It needs to store an address. And this is where this star comes in, because we're saying we're dereferencing. We're saying, go to the place it points and store this value. So we follow the line and we store the value here. Then we do the second calculation. I haven't bothered doing it. Let's just say it's 4. And then my function ends. Okay, so then I go back to main. So all of this is gone now. Okay? Because I have no link to it. But my values up here are now the result. So I've been able to return more than one thing from my function.
Okay.
Does that make sense?
Yeah, but when I compiled it, I did the same thing as in what you did in complex multiplication. And adding ampersand, is that 3 real, is that 3 imaginary? But I was getting an error in the compilation. It said too many arguments.
Okay, so the too many arguments has nothing to do with the pointers. What do you think that has to do with?
Undefined arguments, I suppose.
No? Okay. So arguments are basically these, okay? How many is there meant to be?
6.
Okay, and we know that because of our function and our function prototype. So if you're getting too many arguments, you're trying to put 7 or 8 or more than 6 in. If you get too few arguments, you're trying to put too few in.
Mm-hmm.
So the error is exactly what it says, is that there is too many arguments. So go back and count how many you've got there.
Okay.
Okay?
I'll try some other things. I'll see how that goes. Yeah. Thanks.
But yeah, the error is telling you what the information is. Any more questions? What are windows? Check that window and check
Also, regarding the same task 2, I was also having trouble with the operations and the user to choose the operations if it's plus, minus, divide.
that's what was wrong with that? Was it always choosing the same one, or?
Because I was having trouble choosing the type specifier, so I went. I wasn't sure which type specifier to go. So if it's car, don't you go %C?
Yep.
Or
Yep. So one common mistake that I saw a lot of people do in MATLAB is if you have scanf, %f, and then let's say x, and then after that I do scanf, %c, and y. Can I guarantee that I know what that character is? A better question. Let's say the user enters 4.6 and then they enter A. Or even better, let's do plus. What gets stored in X?
4.6.
4.6. What gets stored in C?
Plus.
No. So this is where a lot of people make the mistake. What character is here? The new line character. Okay, because you press enter. So if you're going to use scanf after you've collected a value, Okay, so if you've got a value beforehand, so %D, %F, or something like that, the best way to handle it is to have a space and then %C. Okay?
Right.
Now, when I went through the debugging stuff, you should be having a look at what this Y actually is as well. So printing it out would have helped in solving that problem. Does that make sense?
Yep.
Cool. Josh is back. Josh.
Yes.
Yes. How you going?
I am well, thank you. How are you?
I don't know. Yeah, not bad.
Not too bad.
Not too bad.
That's good.
Is there anything you want to go through? Your quiz or anything like that?
Not that we
Or
haven't
the last quiz?
covered or hasn't been covered. I can have a look at the
Is there
last.
anything? Have a look at the stats for the last one.
Yeah, I'll have a quick look. I mean, I'm sure a lot of people listening today will be mainly concerned with the assignment anyway. But
Yeah.
we'll have a look.
I'm just staying up. That's why I'm staying online, because I know people are doing it at the same time.
Yeah, you're a nice guy.
Oh no, I am. If you want to go, you can.
I don't mind. All right. Everyone got 100%. So.
Really?
Yeah, it's too easy for everyone. 100%. So. I was kidding.
Definitely, Josh.
So this was quiz 8.
Yep.
Yeah, a lot of people got around the 8.5 to 9.
Oh, cool. Statistics.
Making them too easy now.
Yes. Wait. Average grade of all the terms 59.338. Oh, average of last is 63.95. See if there's any really. Oh, that one's bad.
Which one?
That one's bad. They're the two worst ones, and that one's kind of. Yeah, that's. So these are the ones that are under 50. So.
Which ones are you looking at?
So the first one is week 8 F6, F7, and S4.
Okay. So let me just open those up. I'll share my screen. Questions. Alright, so what did you say? We had week 8, F6, F7, and...
So F6 had around 30% pass, and F7 had about the same, and then S4 was about 40%.
Okay.
And I'm going to be right back.
Sure. I'll open those off my screen. Wait, what was the last one you said? Yeah.
S4. S4.
S4, okay. you want me to start going through them then?
Yeah, you're on the screen.
Oh, I'm sharing. Okay. Show that. All right. So this was one of the questions that people didn't do too well on. So what value would the following return? strcmp, granite, and granular. So remember when we're using string compare? Well, this is what it is. We're comparing two strings. So we talked about we can't actually compare strings by using the double equals. We're not allowed to use this. It won't give us what we're after. So what we have to use is we have to use a function string compare. So again, when we use string compare, we have for string compare, we have two arguments. So in this case, it was granite and then granular. And the question's asking, what will string compare return? So when we're using string compare, it can return three different kinds of values. So it will return a negative number if granite comes before granular in lexicographical order. So that just means if both of these words are in the dictionary, which one will come first? So if these words are exactly the same, it'll return a value of 0. And if this word here comes after this word in the dictionary, it'll return a positive value. So when we're using this in our code, if we want to check for equality, normally we'll do something like this. So we'll check if it's equal to 0, and that'll tell us if these things are equal. If we want to see if this word the first word comes before the second word, we check if it's less than 0. And if we wanted to check if the second word comes before the first word, we check if it's greater than 0. So in this case here, we can see granite, G-R-A-N-I, comes before U. So this here, when we call string compare, we should return a negative integer. So we should get A as our answer for this one here. For the next question, this one here, we see that we're using slightly different for our function. So instead of calling strcmp, we have an n in there. So what that does is, what that means is we have an extra parameter to our call. And what this means is it'll compare, in this case, the first 4 characters. So that's what this last number represents, the number of characters we want to compare. So in this case here, we're comparing the same words, except what the number 4 does, this just means we're only comparing the first 4 characters of each of these strings. So we can see they're exactly the same here, G-R-A-N and G-R-A-N. So because they're the same, this will actually return a value of 0 in this case. So that's how the string compare and the string n compare functions are a bit different there. See, we should get C as our answer for this one. And finally, one more question that people sort of struggled with. This one here. So we're talking about structs in this case. And the question was, the following will produce at least one error or warning. So we've got a struct definition, and we can see that we're talking about a struct here. When we say S1, that's the same as actually saying, if we had a struct and the struct actually had a tag as well, we'd actually be saying we want to create a struct or a type with S1. So then we can talk about S1.height and all those sorts of things. You can see that with this struct here, normally we see struct car or struct gear, like what we were doing in the labs. But in this case here, we don't actually have a tag. So what that means is it kind of doesn't seem like we can ever create a struct of this type because we can't actually talk about the struct. And this is very bad programming practice. You'd always have a name here for your struct. So struct gear, for example. But this is actually legal. So because we're saying S1 here, this means we want to create a struct or this kind of struct. So we can actually talk about it later. If we didn't have this S1 here, then we'd have absolutely no way to ever create a struct with these members. So again, it's terrible programming practice and we'd never do it this way, but it's actually legal to have code like this. But it means that we could never create another one because we can't actually talk about it because it has no tag. Does anyone have any questions for those that are listening on that? Either of those few questions that we've been through? Most people did fairly well on the quiz.
Josh, I have a question. Hello, can you hear me?
Yep.
Yeah.
Yeah.
So strncmp, granite and granular, 4 will check first 4 letters.
Correct.
Is there any way out to check from end of the string?
What's that, sorry?
Is there any way out to check the last letters of the string?
So say if we want to compare the last 4 letters?
Yeah.
Is that what you're sort of asking there, if we want to compare the last 4? Yeah. So using this function, we're not allowed to actually do that because it will compare from the start of the string. If we wanted to kind of manipulate it that way, we could use our other functions to create a substring. So we talked about those last time, how we can actually create substrings of these functions. And then we could use those substrings and do a comparison on those. Normally when we're doing a comparison though, we're normally looking for the start of the word. There wouldn't be very many times that we only want to compare the last few characters. But if we did, we'd use...
It's actually easier to compare the last number of characters because you've got the null terminator. So if you start the string from, say, the last, from 4, because remember they're pointers, so you can just add the addresses, it's going to stop at the end of the string. The reason there's the string end compare is purely because you need to stop where there's not a null terminating character. So Josh could pass 2 pointers and then add 4 to them or something. And then compare from that point on to the null terminating character, or from the middle of the string up to 4. So the string end compare, what you could do is something, so you've pretty much got all the flexibility to, string, why am I writing sideways? Sorry, my tablet's sideways. What do we do? String. I don't know why I'm writing num. If you've got string in compare, and I've got, what were your 2 strings, Josh?
Granite and granular.
Granite and granular. If I wanted to compare from here to here, let's say, and I wanted to compare it to here and here, string and compare is pretty flexible. Let's say this is pointer 1 and this is pointer 2. So I can compare pointer 1 plus 3, pointer 2 plus 4, and then do 2. I think I'm not on the screen. So I can use string and compare to compare anywhere. If I wanted to just look at the last ones, I wouldn't even need to do that. I could just add to my pointers and point, say there. And then that would just look at the last couple of letters. Because you've got the null terminating character at the end, it will look at the last one. So the last couple are actually really easy because you just go up to a certain amount and then just look at it until it reaches the null terminating. If you need to look at the middle, then you just specify up to that point and then how many. So the reason that there's an N version is because the normal versions are looking for that null terminating character. Does that make sense, Ila?
Yeah, thanks.
That's all right. Yeah, they're pretty flexible. Damn you not having your notifications on.
Trying to beat the screen.
Pardon? Yeah, I was trying to go
You were trying
the
to.
screen.
Yeah. You would.
All right. Is there any more questions for...
What is that sound? I'm so confused.
What sound?
That popping sound.
What popping sound?
Is it like your water bottle or something?
What popping sound?
The sound that you've been making all night.
What sound?
It goes like tunk, clunk, clunk. Yeah, whatever you...
Happen?
Huh?
That?
Not now, but whatever you're playing with is what's causing the noise.
I'm not playing with anything.
Uh-huh.
I don't know what you're talking about.
Uh-huh.
Have we got any more questions about this? That's my drink.
Yeah, that's what's being
My
caused.
Gatorade. My
Oh,
Gatorade.
really? Get those electrolytes?
Yep. Oh, it's the top of the bottle. Yeah. We've been doing it to annoy Antonio.
That's fair, yep.
Yeah.
I'll start tapping as well, actually.
Okay. Is anyone likely to have any more questions about the assignment? Are we happy to end the stream? Okay. Who's here? There's not much point. All right. That's all right. Once again, before you go, if you can do that survey, I appreciate it. It helps us out to do stuff like this. All right. Thank you, everyone, for coming. And end.